Hey, Algebra 2, here we are in Chapter 13. We're looking at 13.7, Inverse Trigonometric Functions. Our vocabulary today is so much better looked at in terms of the concepts in the text that I took a couple pictures so we can discuss it and kind of look at it together. So the first one, principal values. Remember, we're still talking about sine, cosine, and tangent. We're still talking about trigonometric functions, but now we're going to really talk about them as functions and also refer to their inverses as the title indicated. So if we were to think about, let's say, the sine function and its inverse, we can see that its inverse is not a function. And so what happens is when we think about, like if you were to, and we've done this in geometry, we've done this already, when we need to do the inverse sine to find an angle, we only get one angle. We don't get infinitely many angles, as would be implied by the sine function. So what ended up happening, or what the decision ended up being to refer to principal values, is to consider a chunk of the sine function where you can get all possible values of the sine function, like all possible ratio values. If you think about it, you can tell that the ratios that are represented by the sine, or the sines of different angles, all the different ratios go from -1 to 1. And so this was a convenient chunk of the sine curve to think about in reference to the sine function, which this function is now defined as a capital S, sine of x, and therefore the inverse sine, now this is an inverse sine equation, which is not a function, but if we want to consider the function, it would only go, just as, let's start here, this function, the actual sine function, has a domain of -pi/2 to pi/2, and it has a range of -1 to 1. Whereas the inverse function would also have or inversely have a domain of -1 to 1. But then, since we're truncating it, since we're cutting it off, since we're only considering principal values, we would stop it here. Make sense, guys? I hope so. So this would be a proper function to the inverse function, as it would pass the vertical line test. Remember, functions do not have a functional inverse if it doesn't pass the vertical line test. All functions do that. And the horizontal line test, which lets us know that a function is 1 to 1. All right, let's go on. So in this section, what we're seeing is that similarly, just as we had to redefine sine as y is equal to capital sine, so we only got that little piece of sine, then we can talk about the fact that y capital sine is really y lowercase sine, but truncated from -pi/2 to pi/2, the principal values we're going to be talking about. Similarly, we can talk about capital Y equals capital cosine, y equals capital tangent. And so we had to truncate it so that we just got a little piece of it that is representative of every possible value or every possible ratio we could have of these trigonometric functions. And so that's what's happened here. Notice that cosine has a different domain of 0 to pi, and sine has the same domain, capital tangent rather, has the same domain as sine, -pi/2 to pi/2, but not including the -pi/2, because you remember, if you looked at the graph of the tangent function, do that now if you haven't, you'll see that the tangent function has asymptotes, and those asymptotes are actually located about pi distance apart, but every pi/2. So you'll see something like that. So you can see that the function arcsine function that is symbolized in either of two ways, this way, inverse sine, or using the word arcsine like that, the arc, or the abbreviation arcsine because the E's not there. So using either of these is channeling or is pointing to this particular graph where the domain is from -1 to 1. Remember, this is the inverse, and the range is from -pi/2 to pi/2. So here we're asked to solve for the capital sine of x of the square root of 3/2. Now I point out this capital sine because we're just dealing with that limited truncated function, the smaller piece of the sine for a curve. If you were to be asked this and it was a lowercase s, sine of x, something like that is equal to this, then you would need to know or account for the fact that there are infinitely many solutions. And obviously, we wouldn't write them all out, but we'd have to account for that. We don't have to do that here because this capital S gives us permission just to concentrate on the domain from negative pi over 2 to pi over 2. So this implies this. We're looking for the arc sine of the square root of 3 over 2, and that's going to give us x. That's going to give us that angle. And the answer to the nearest degree, so we know that we're dealing with degrees here. What I want you guys to do is see if you can guess the answer without using your calculator, because we don't need our calculator right now. Hopefully you're remembering the unit circle. You could think about the unit circle. You could also think about charts. Remember the charts that we've been doing. All right, if you don't remember, the answer is going to be 60 degrees. Sine is, the sine of 60 degrees is equal to the square root of 3 over 2. So x is equal to 60. Yes, you could have grabbed a calculator and done this. I know you guys know how to do it. But yeah, we got to start using our memory. Let's look at another example. Example 2 is pretty neat. Let's take a look. Apply an inverse to solve a problem. Look at the picture as I read. Each leaf of a certain double leaf drawbridge is 130 feet long. If an 80-foot wide ship needs to pass through the bridge, what is the minimum angle, theta, to the nearest degree, which each leaf of the bridge should open so that the ship will fit? So in my mind, I decided that I was just going to make this ship bigger. Not so much taller on purpose, but just for me to have a perspective. My goal is that, notice I made it so that whatever's happening on this ship, it's 80 feet wide even at the top, or at least I have to consider that. This way I'm not considering, well, maybe the levers can be so low that it can escape through. So I'm just assuming that, hey, the whole ship is 80 feet all the way up to the sky, and we just needed to pass through. So that helps me have fewer variables to contend with. So focusing right in on these little triangles here, I'm going to drop this perpendicular right down here and just assume that we know that we've got to be at this angle, so from here to here is 40 and from here to here is 130. So we need this distance. I don't know if this is making sense to you guys, but we need this distance from the top of the lever to the bottom, right? This distance, if we were to drop a perpendicular there, we need this to be 90, as this half would be 40 for the ship, right? All right, cool. I think you guys are with me. So now basically what we're doing is finding this angle given the 130 and the 90. And we also have the same thing here. It would be the same thing without too much more calculation. So this would be the correct angle for both of them. So what is this when we have adjacent and hypotenuse? That would be cosine. Let's use a better color now. So that would be the cosine of theta has to equal 90 over 130. And so we're dealing really just finding the inverse cosine of 9 over 13, which we can do with the calculator, which we can do with Desmos, which we could do with our cell phone. So I recently downloaded one of these Silver Edition TI-84 Plus versions to share with one of my other students. And so I just thought I'd show it to you guys. I know we don't always use this type of a calculator. So the first thing I'm doing is making sure that I am in degree mode. And you can see the larger screen here. And so once I'm in degree mode, I'm going to go back and clear this off. And I'm going to get started. And so what I need to do is find the inverse of 9/13, and wanted that to be in degrees, and so I get that it needs to be approximately 46 degrees. I'd say, yeah, 46.2 degrees. So that's our theta value to make sure that the ship can pass. All right, so here's our final example, and you'll notice that the answers are there, and part of it is I had this scheduled as an in-class event for us to do, and so I wanted the answers there while you guys made sure that you could use your calculator to get the correct answer. And it's okay, the answers are there. It should just make sense as to how we do it. So notice we're going to need a calculator not because of the angles right now, but because of the question. Find each value, write the angle measure in radians, and round to the nearest hundredth. So this little piece reminds us that, okay, we're looking for a decimal answer. Even though we actually did this problem before, we remember that this would give us an angle degree of 60 degrees, and we know that we can write 60 degrees in radians as pi over 3. However, we need a calculator to either just do the arc sine of square root of 3 over 2 and then get this answer here, or if you remembered the pi over 3, then you can use pi over 3 and see that the pi over 3 is equal to 1.05. Because if you think about pi, you know what it is, 3.14, blah, blah, blah. If you divide that by 3, you get, 1.049 something or other, or something. All right, so this is what we want because we're rounding it to the nearest hundredth. This one looks crazy though, right? So what is happening here? So first of all, we are looking for an angle. We're going to find the tangent of an angle. What angle? The angle that would give us 6/7 as its ratio when we find the cosine of that angle. Ooh, lots going on here. What we need to do is first find the inverse cosine of the ratio 6/7. Once we have that angle, then we can find the tangent of that angle. Notice that cosine is capitalized, so we're not looking for any angle that gives us this 6/7 ratio. We're looking for a specific angle within the domain of cosine, capital cosine function, which is from 0 to pi, which is not going to be hard. Our calculator will automatically give us that. However, I just want you to be aware, and then we take the tangent of it, all right? So I'm going to go and grab our calculator. And you all know you don't have to have this calculator. I just thought it was neat that I had access to one, so I thought we could hang out with this for a little bit. So we're finding the inverse of 6/7, and of course you could do this on Desmos, even your cell phone calculator. When we find that, we get 31 degrees. And I could actually keep going with this, right? But I'm remembering that we were talking about sine. We were talking about everything in radians. So I could honestly just do that, find the tangent of the answer that I just had, the solution. So it's, let me go back here and just find the tangent of that. Hold on. I could have just plugged it in all the way. Let me go over here and insert tangent there and find the tangent of the inverse cosine. I guess I should have done it all together. Find the tangent of the inverse cosine of 6/7. I could do it, and kind of, honestly, it doesn't matter what, if I'm in radians or degrees, because ultimately I'm just looking for a ratio of this situation. So when I do that, I end up with this as the ratio, 0.607. But what I want to show is that even if we change the mode, even if I went into the mode and I said, oh, I want to be in radian mode, right? Let me go back this way. And I did it, I should get the same value. That's really the whole point of sometimes we can circumvent that. So if I go here and then I clear that off and I do the exact same thing again, and so I basically got the calculator to repeat it. It's going to be pretty anticlimactic, but you're going to see the same answer even though I'm in radians, because in this exchange I didn't actually have to find the angle. So the final answer for this is 0.60. Let's see if I round this up. Yeah, 0.60, I think, rounding it to the nearest hundredth. Just like the answer was here. I forgot the answer was there, guys. All right. So with that, this is all we really need to do. A lot of this was just calculator work, literally just plunging it into your calculator. And here I'd use my memory for part of this, but still, again, calculator, you could have done that. Let me know if there's any questions, whether on the device that you're using, how to put in square root of 3, whatever it is that you might be having difficulty with. All right, guys, that's it for me. I look forward to talking to you soon. Take care.